Hello everyone, welcome to today's class. This is Teacher Simon taking you through Cambridge International AS and A-Level Chemistry for Feb March 2025, and this is part 2 for questions 26 to 40, and this is organic chemistry. Question 26, organic compound X has the empirical formula C2H4 or compound X is reduced by lithium aluminium tetrahydride but not sodium hydrodoborate. What is compound X? Now, since this one cannot be reduced by sodium hydrodoborate, but can be reduced by lithium aluminium tetrahydride, then it must be a carboxylic acid. Okay, must be a carboxylic acid. So we are seeing a carboxylic acid here and then here. Okay, so ethanoic acid is CH3COOH. That means its molecular formula is going to be, let me just write MF here. Molecular formula is going to be C2, then hydrogens are 4, and then oxygens are 2. So meaning empirical formula is going to be, if you divide all through by 2, because empirical formula represents the simplest whole number ratio for the number of atoms which are present in a given compound. So we shall have C, then H2O. So you can see that this one doesn't match with the one that is given here. So that means this one is wrong. But then when we come to butanoic acid, we are going to have CH3, CH2, CH2, and COOH. The molecular formula is going to be C4, hydrogens 3, then 5, 7, then 8. So we shall have H8 here, and then oxygens are 2. Then when we come to the empirical formula, we will divide all through by 2, so it will be C2, then H4, and then O, which corresponds to this one that we are having here. So that means our answer is this D, butanoic acid. Question 27. What is the mechanism for the reaction of hydrogen cyanide with propanone? Now the mechanism is actually like this. You have propanone, which is CH3. Then we have the carbonyl carbon there. And then we have the CH3. This is propanone. So hydrogen cyanide, I'm going to take the cyanide, CN. It has a negative charge here. Then the lone pair here comes to this carbon here. But this one has to be partially positive. And then the oxygen being more electronegative than carbon, it has to have a partial negative charge. So when these electrons come to this carbon, then this pi system is going to be broken down. And then we are going to have CH3. Then C, then O with a minus here, and then we shall have a CH3, then this cyanide here attached to this carbon. Now this oxygen has gotten a lone pair here, so it donates it to a hydrogen here in the cyanide. Okay, and then this one here has to break off. Then you will get CH3, then C. The compound that is formed here, we call it the hydroxynitrile. Okay, hydroxynitrile. So hydroxy is the OH, then the nitrile is that CN. Now, what we have added on here, you can see that we have added on something, the cyanide. Okay, and it is it has electrons. It is full of electrons. Okay, so it is a nucleophile. Nucleo means it wants the nucleons. It loves. Philic means love. Okay, nucleophiles. In the nucleus, we are having protons and neutrons. If we have protons and neutrons, these ones are positively charged. These ones don't have any charge. So something that loves the nucleons must be negatively charged, such that it bonds with the protons in there. You get it? So that therefore implies that this one must be negatively charged. Okay, so it's a nucleophile. So therefore, what we are going to have here, it is a nucleophilic addition. Okay, it's a nucleophilic addition, so the answer has to be a C. Question 28. Which compound may be synthesized from an alkene with the formula C4H8 by an addition reaction? C4H8, that is butene. It can be but1-ene or but2-ene. So if I maybe begin with but1-ene, this is CH3, CH2, then CH, and then a double bond with CH2. Okay, now since we are having 1,1 dibromo, that means we are adding bromine. Okay, so if I add bromine, we are going to have this bromine molecule here. Okay, and then since the two bromines here have the same electronegativity, there is no charge. Okay, the dipoles cancel out. But as this molecule comes closer to this molecule here, this alkene, remember electrons are negatively charged. So when it comes around this electron cloud, it is going to induce a partial positive charge on this bromine that is nearer to it, and then a partial negative charge. So now electrons will move from here, then they come to this bromine here, and then this one will be broken off. Then we shall have the CH3 here, CH2. Then here we are going to use the Markov's rule, which is based on the stability of the carbocations. So I usually say that the rich get richer. So the carbon with more hydrogen atoms is the one that gets the electrophile here first. So we shall have the CH, then CH2 here, then Br. Why is it like that? Because we have this one is going to be positively charged, so there is an alkyl group, and this one is also an alkyl group. That is a secondary carbocation, which is more stable compared to if I had this one, the CH3, CH, maybe the Br attaches to it, and then CH2, then this one with the plus. This is one alkyl group. So that is what we call a primary carbocation, which is not stable as the secondary carbocation. So that's why we say the rich get richer. So this one with the more hydrogen atoms gets the electrophile first. Then this bromine that has broken up from here now is fully negatively charged. So it is going to now donate the electrons to that. And then we are going to have the CH3, CH2, then CH with a bromine here, and then CH2 with a bromine here. This is one, it is on the first carbon here, then this one is on the second. That is 1,2-dibromobutane, and we can see 1,2-dibromobutane here. So this one can qualify this to be our answer. But this one being from butene, that is but1-ene, but we also have but2-ene. Okay, there is but2-ene, CH3, CH, then double bond CH, and then the CH3. Okay, so this one, when we add bromine here, then we are going to get CH3, CH, you get a bromine here, CH, then you also get a bromine here, CH3. You see, so this will be 2,3-dibromobutane, and we are not seeing any 2,3-dibromobutane. Okay, how about this one here? This one is coming from an isomer here. Okay, we can cut off this using chain isomerism, and then we put this one here. So when we do so there, we are going to have, of course, the hydrogen which is here is going to shift and then comes to that one there. So we shall have CH3, then C, and then the CH3 here, then a double bond, then we shall have a CH2 here. Okay, hydrogens are 8, the 3 plus 3, then plus the 2, and then the carbons are 4. So that is another isomer there. Then if we add bromine again here, we are going to have just attach a bromine here and then there. So we shall get CH3, C, Br, then CH3 here, and then CH2 Br. Okay, so this one is going to be 1. This is a methyl. This one is a methyl propane. Okay, because we cannot have like, you cannot say that this is 2-methylpropane. Okay, because you cannot have 1-methylpropane. You cannot shift this one and then put it here. Now it will, the longest chain, the longest carbon chain is going to be now with the 4, so it will become a butane. Now what I'm going to have here is, this is on the first one, then on the second one, so that will be 1 2. This one will be 1 2. Okay, dibromo, 1 2 dibromo methylbutane. Methyl, I mean propane, not butane. But here we are having 1 3 dibromo, yet we are supposed to have this one here, you see. So meaning our answer is this B, which is 1 2 dibromo butane. Question 29, the structure of compound G is shown. This is the one here. Compound G undergoes addition polymerization. In most cases, for addition polymerization, we use alkenes. Okay, for your AS, we use alkenes. So what you can do, you can spread the 2, just get those 2 carbons in the double bond. So you have this and this one here. We are having them here. So one has gotten 2 hydrogens. Then this other one here has gotten a cyanide. I can even just leave it just like that. And then this other one has gotten an ester here, COOCH3, like this. So what happens in the addition polymerization, the pi system here is broken, so you open it up this way, and then you also do it that way. Then you are going to form something like this. And then we have the CN, then the COOCH3. Then you open this, and you also open this. So this is the repeat unit of this kind of polymer. Okay, so when we look through what we are having here, which one represents, we are not having any double bond in here. Okay, so A and B are off, and I think that has to be C. It is this C here. So you can see the CN that I'm having here, and then the COOCH3, you can see it there, and then the CH2. So our answer is C. Then question 30, compound T is treated with 3 reagents and gives the results shown. And the reagents, we have 2,4-dinitrophenylhydrazine. If it gives an orange precipitate, that means it is either analdehyde or a ketone. In other words, a carbonyl compound, because they are the ones that give the positive test with 2,4-dinitrophenylhydrazine. Then with failing solution, no reaction. So if there is no reaction with failing solution, that means this is a ketone. Okay, it's not an aldehyde, because aldehydes give a positive test with failing solution and Tollens reagent. Okay, but ketones don't. So since there is no reaction with failing reagent, then we are talking about a ketone. Then acidified potassium dichromate, this is an oxidizing agent. So if no reaction, then that means there is no oxidation. But if you check what we are having here, we have an aldehyde. This one can be oxidized. Okay, so because it can be oxidized by this dicarboxylic acid, then this one is off. You see that? And also this one is a primary alcohol. It can be oxidized by this acidified potassium dichromate to an aldehyde, then later carboxylic acid. So even this one is off. Then this one can be oxidized because it is a secondary alcohol here, and it can go to a ketone. So even this one is off. Okay, but then this one here, it is CH3, then C, we have a hydrogen here, then we have another methyl group. Actually, let me put the methyl group down here, and then maybe the hydrogen here. Then we have C, then double bond, and then this one here. So since this one is a ketone, it cannot be oxidized by this. Okay, It cannot be oxidized by this, and it will give a positive test with the 2,4-dinitrophenylhydrazine, and it will give a negative test with Fehling's solution. So that means our answer is D. Question 31. Reagent X is added separately to 2-methyl-butane-1-O and 3-methyl-butane-2-O. The visible results are different. So let's first draw these structures here. 2-methyl-butane-1-O. So 2-methyl-butane-1-O, this is an alcohol. So this is 1, 2, 3, 4. Okay, butane 1O. So I'll put the OH at the end here. And then they said 2-methyl. So the methyl group is going to be on the second one here. That means here we'll have one hydrogen, and then here CH2, then here CH3. Okay, this is the one here, 2-methyl-butane-1-O. And then next, we are going to have this one here. It's butane 2O. So I'm going to just copy this one here, put it here, butane 2O. So 3-methyl. Now, this simply implies that we are going to take this one off, the methyl group. We shall put it on this one here. Then the OH, I'm going to put it away from here. Then I put it on the second one here. Okay. So this is CH3 now. Then we bring this one here. I think it will be like that. So it's an alcohol. So this one is a substituent here. So the counting is from this functional group. Okay. It is the one that is to take the least number. So this is 1, then 2, then 3, then 4. Okay. So like that. Now they are saying which reagent is going to give two different what? Results. When you react with sodium, alcohols react with sodium to get sodium alkoxides. Okay. In other words, this one goes off and then you put there the sodium. Okay. And then hydrogen as a gas is released. So both of them will give a positive test with sodium because they have the OHs. Okay. Then next, we are having alkaline iodine. This one gives a positive test. Since these are alcohols, an alcohol must have this group here, CH3CH, then OH. If this group is available for any alcohol, in other words, that secondary alcohol, then it can give a positive test, and that positive test is this. Actually, this one we call it the iodoform test. Okay, so CH triiodomethane, this one here, which is a yellow precipitate. Okay, so when you look at this one doesn't have this CH3 CHOH group, but this one has it CH3. You see the group here. So that one will give, you see? So that means this is the answer actually, because this one gives a positive test with it, but this one doesn't, you see? Then PCl5, this is a substitution reaction. Alcohols can be converted to chloroalkanes by reacting with PCl5 or thionyl chloride or PCl3 with here you have to accompany it with heat. So, and then you get this OH substituted by the Cl. Okay. Then the last one, acidified potassium permanganate. This is this one is an oxidizing agent, so it can oxidize this one to an aldehyde, then later to a carboxylic acid. The same thing, this one can be oxidized to a ketone because it's a secondary alcohol here. You see that? So this one will give the positive result for both of them. So the answer is therefore this B here. Question 32. Compound Y is hydrolyzed by warm aqueous silver nitrate to form a precipitate that is soluble in dilute aqueous ammonia. Compound Y undergoes an elimination reaction to form an alkene. Okay, what is the skeletal formula of compound Y? Now, when we put these compounds in aqueous silver nitrate, let me reduce this a bit. We are going to weaken this bond here, and all of these halides are going to be released in the solution. So you are going to get the halides in here in solution. We know that chlorides, okay, chlorides, they are soluble in, because now we are putting in aqueous ammonia. So in dilute and concentrated ammonia solutions. Then the bromides are insoluble. Okay, they are insoluble in dilute ammonia, but soluble in concentrated ammonia. Then we have iodides. For them, they are insoluble in dilute and concentrated ammonia. Okay, so since they said that aqueous silver nitrate, then to form a precipitate, the precipitate can be, of course, silver chloride. That one is a white precipitate. Silver bromide, that is a cream precipitate. Then silver iodide, that is a yellow precipitate. Now they are saying that is soluble in dilute aqueous ammonia. Soluble in dilute aqueous ammonia, we see it with the chloride. Okay, bromides, they don't dissolve in dilute ammonia, neither do iodides do so. Okay, so therefore our answer has to be with the chloride. Okay, then they are saying that compound Y undergoes an elimination reaction to form an alkene. So I'm supposed to center on these ones here. Now when I look at those two here, an elimination reaction, that means we are going to use something like sodium hydroxide. We must use sodium hydroxide, a very strong alkali, in ethanol. Okay, in ethanol. Then you convert a halogenoalkane to an alkene. So let me write the structures here. Then for C, we are having a CH3, then CH2, 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 Cl. 1, 2, 3, 4 carbons. So these are the ones that we are having there. And then next, this one here, there is this carbon here. It has 3 methyl groups. Okay, 3 methyl groups. So we have CH3, then C, there is a CH3 here, and then there's another one here, and then there is a CH2 here, then a chlorine. So for elimination, what happens is that the carbon that has that halogen, the halogen is lost, and then we go to a carbon which is next. Okay, a carbon which is adjacent to that carbon holding the halogen. This carbon here must lose a hydrogen. Okay, now when you look at this one here, this one can go, and then this one loses a hydrogen. So you will have CH here, then a double bond, CH2. So you get an alkene. But then for this one here, you can see that there is no hydrogen on this carbon which is adjacent to this one, which is directly connected to this one holding the chlorine. So there is not going to be any elimination here. Okay, so the elimination is going to take place with this one here. Okay, elimination is going to take place here. So that means our answer is going to be a C. Question 33. Propan 2O can be converted into 2-chloropropane using reagent M followed by reagent N. Which row is correct? Now the reagents we are given here, we can see concentrated sodium hydroxide, then sulfuric acid. When we use concentrated sulfuric acid or concentrated phosphoric acid on an alcohol, it is going to dehydrate it. Then you will get an alkene. Okay, then when we get an alkene and then we react with, let's say, chlorine, we are going to form, this one will give us propene first, then we can put chlorine and then we get 1,2-dichloropropane, you see, but we want 2-chloro. It's not a dichloro, it is just a 2-chloropropane. That means we can use HCl. So the answer is actually likely to be, if it is sulfuric acid, then we must have HCl, but here we're having chlorine, so that is off. So the answer has to be this C here, concentrated phosphoric acid, and then with the HCl. Okay, but you have this CH3, C OH, then HCH3. I can convert this one directly, okay, to the 2-chloropropane by using PCl5. Okay, it's a substitution reaction. Okay, directly PCl5. You can use SOCl2, you can use PCl3 under heat. Okay, but then since we are using two reagents here, that means I can first convert this one to an alkene, so it comes to CH3, then CH, double bond, CH2, then later I react with the HCl. So the hydrogen will first come to this one here, and then it forms the CH3 here. Then the chlorine will come to this, okay, using the Markovnikov's rule. So that is how this one can come about. But to convert this alcohol to an alkene, I need conc sulfuric acid or conc phosphoric acid. Okay, so that's why I'm taking the third one here, where there is the HCl at the end. So that is conc phosphoric acid. So this is our M, this is our N. So the answer is that C. Then question 34. Skeletal formulae for 4 organic compounds are shown. And then you are saying which 2 organic compounds, when separately heated with dilute sulfuric acid, produce propanoic acid as one of the products. So this one here is an aldehyde. We don't know that reaction between an aldehyde and then sulfuric acid. Okay, so my one, this one here has to be off. But then when I come to this one here, it's an ester. So 2 being an ester, always focus on this carbonyl group there. So this part here provides the carboxylic acid. So this one is going to be the CH3, CH2, COOH. So there is propanoic acid in here. Okay, it is hydrolysis. And then here, this is ethanoic acid, the one that you will get from here. This is ethanoic, CH3, and then the COOH here. Okay, when you rush with this one here, this is an alcohol, CH3, CH2, CH2, then OH you will get here. You see? So, meaning that 4 is off. So, wherever there is 4, we can pull it off. Okay? So, 4 is off. This one is off. How about this one here? We are used to having nitrides which are hydrolyzed by dilute HCl. Okay? Dilute HCl, and then here you'll have the CH3, then there is a CH2 here, then there is the carbon here, then it will be hydrolyzed to the carboxylic acid. Okay, then the other inorganic compound that we get from here is ammonium chloride. Okay, but now since we are using sulfuric acid, dilute sulfuric acid, it is going to work the same way as dilute HCl. So instead of getting this one, then I'll get ammonium sulfate as the inorganic product, okay, byproduct that comes off from there. So this one gives us, and this one gives us. So that means our answer has to be with the 2, okay, and the 3. So that is C. Question 35. 1-chloro-2-methylpropane and 2-bromo-2-methylbutane react separately with aqueous silver nitrate in ethanol. So let us first draw these ones here. So I have chlorine, I can write it first here, then CH2, then I have CH here, and then CH3. Remember it is propane, so methylpropane. Then the methyl group has to be on this one. It cannot be here. That means you're going to have the longest chain will be with 4 carbon atoms, and that will be butane. And then the other one is 2-bromo-2-methylbutane. So we have 1 2, 3, 4. It's a butane. So CH3, then I'm saying 2 bromo, then 2 methyl. Okay, so I can say CH2, then CH3. That's what we are having there. Both reactions proceed via nucleophilic substitution and a precipitate is formed. Now, when you look at this one here, there are 3 alkyl groups. There is this one here, there is this one here, and they have a greater positive inductive effect. Okay, so, and also this one here. So since this one is a tertiary halogenoalkane, it will proceed via SN1. Okay, SN1, where one species is the one that is responsible for the start of the reaction in what we call the slowest step. Okay, in the slow step. So where this one gets off. Okay, but then this one here is a primary because this is one group here. This is primary. So since it is primary, then that means this is primary, this is tertiary. So this one will go via SN1. I mean SN2, sorry, SN2. So, and then another thing, they are saying that the time taken for 1-chloro-2-methylpropane to form the precipitate. So the precipitate here, remember you are using aqueous silver nitrate, which weakens the bond, the carbon to halogen bond, okay? Then this one is released in the solution. So that means, of course, we know that these bonds here, now here we are having chlorine and bromine, sorry. This is bromine, and then the chlorine here. So which one is stronger? Okay, so you can see that this bond here, since chlorine is more electronegative compared to bromine, okay, and it is smaller in size, okay, because it is smaller in size, this bond here is shorter than this one because this one is bigger, okay. So this bond here, the longer the bond, the weaker it is. So this one is longer, the longer bond, and this one is a shorter one. So this one is strong and this one is weak. Okay, so weak, this one is strong. Now it is going to take much more time to break this one compared to this. So that means for 1-chloro, if it is T1, the time taken here, T1 must be greater than T2. Okay, so the time taken to break this one here has to be very small. So T2 is less than T1. You see that? So which row is correct? First of all, this 1-chloro-2-methylpropane undergoes SN2. So there is SN2 here, 1-chloro-2-methyl. You see SN2? Then T1 is greater than T2. That's what I've written here. So even this one is correct. So meaning that our answer is going to be a B. Question 36. The diagram shows the structure of progesterone. This is the one here. Which statement about progesterone is correct? But you can see what is given here. They are talking about chiral carbons. How many are they? You see? And also the molecular formula. So let's find out on the molecular formula. So let me first let's identify the carbons and then the hydrogens here. So there is a carbon here, then a hydrogen, and a hydrogen. There's a carbon, a hydrogen here, a hydrogen. There's a carbon. Let me first put the carbons everywhere. And these corners here. So this is what we are having here. There is a CH3 up there, and there is also another one here. So how many carbons do we see? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 21. So there are 21 carbon atoms. Okay, so that is C21. Are we seeing any 21? So we can see it here and here. You see that? So that means our answer has to be either B or D. Okay. Then next, we can now go to the hydrogens. So here there is a CH3. Here there is no hydrogen because carbon has gotten the 4 bonds. 2 here, 1, and then 1 here. Then next, we can have a hydrogen here to make them 4. And then CH3 here. Then here there is a hydrogen. There's a hydrogen. Then here there is a hydrogen. Here we shall have a hydrogen. Here we shall have a hydrogen and a hydrogen. Then a hydrogen. Then CH3. Then there's a hydrogen here and also here. Then here. 2 of them. There's a double bond. So do we have any? This is 1, 2, 3, then 4. So we don't have a hydrogen there. But this one will have a hydrogen because these are 2, then 3, then this has to be the 4th. Then hydrogen here, hydrogen here, hydrogen here, hydrogen here. Okay, so how many hydrogens are we seeing here? The hydrogens are 3 here. Okay, 3, 4, 5. Okay, 6, 7. Okay, let me repeat this. 3, okay, 4, 5, 6, 7, 8, 9, 10, 11, 12. Okay, 12, 13, 14, 15, 16, 17, 18, 19, 20, 1, 2, 25, 26, 27, okay, 28, 29, 30. So there are 30 hydrogens. So try to clean this one again. So 30 hydrogens. How about the oxygens? Of course, we have 1 and then 2. So oxygens are 2. So do you see that both of them have gotten the same? Now let's go to the chiral centers. So when we go to the chiral centers, we are having, remember, a chiral center is that carbon that has gotten 4 different groups that are attached to it. Okay. Let me even change the color for this one here. There is a chiral center here. So I'm going to put an asterisk. Okay, because this group here is different from what is this way, different from what is, and there is a hydrogen here. Okay, so that is 1, and there is another one. Which other one are we seeing here? So there is this one a chiral center? This one here. All different. That's another one there. Okay, and then we have another one here. Okay, we have another one here. This one has CH2. Those ones are not chiral centers because 2 groups are the same, the hydrogens. There is another one here. Okay, there is another one here. Any other? So how many are those? 1, 2, 3, 4, 5, 6. So there are 6 chiral centers there. So meaning our answer here is D. 6 chiral carbons. Okay. Question 37. A molecule of hexane can be cracked in a number of different ways. 3 compounds are listed. Now, when you crack these long chain alkanes, you are supposed to get, okay, when you crack this, let me just write it here. When you crack this, there are 2 things that you get. You can get an alkane, a shorter alkane, plus an alkene, okay, plus alkene and alkenes. Then you can get only alkenes, but since alkenes involve removal of hydrogen in there from the alkenes, so you're having an alkene and then hydrogen as a gas, okay. Now, when you see what we are having here, there is C3H8. Remember the general formula for alkenes is CnH2n, then plus 2. And this one falls in there. So that is an alkane. Then this one is an alkene. Okay, this is an alkene because it's CnH2n. And then this one is an alkane. Okay, is an alkane. But if this is hexane, and then I crack it, so here if you have C5H12, that means you are having a CH, the other one that is kept off, this is an alkane, so you are supposed to get an alkene, and you cannot have an alkene of one carbon atom, they have to be 2 carbon atoms. You get it? Because this one is 5 and you're having 1 carbon atom, yet they are supposed to be 2 for you to have this alkene. So this simply implies that you cannot have this C5H12. So this one has to be off. But it is possible for you to get the C4H8, okay, in the mixture. They are saying in a mixture. It doesn't necessarily mean that I'm going to have this one plus this one, because now when you look at the carbon atoms, they are going to be how many? The carbon atoms are going to be 7, 3 plus the 4, and yet hexane has 6, okay? So they are talking about the mixture, what is possible to be formed in there. So I cannot form this one because the next one that is supposed to attach to it has to be an alkene, because this is an alkane. You cannot crack and then you get 2 alkanes, only alkanes. You get it? So therefore, I can form a propane and then another alkene, you see? And then I can form this butene, whether it is but2-ene or but1-ene, that's an alkene, and another alkene. No, it can be, yes, and another alkene and then hydrogen, okay? Because I said alkenes and then hydrogen. Or this alkene and then another alkane, and of course the alkane that will be formed in here must be having the 2. That is maybe ethane, 2 carbon atoms, ethane. So it has to be 1 and 2. So that means our answer has to be a B. 38. The diagrams show the structures of 2 isomeric dicarboxylic acids X and Y. Actually, when you look at these two, this group, the same as this one, they are on the same side. And also the hydrogens, this side. So this is a cis, and this is a trans isomer. You see? So this group is this way, and then the other one is this other side. X can be reduced to compound P with empirical formula, this one. So when we reduce this one, the carboxylic acid is going to go to the primary alcohol. So we can have something like this, C, then C here, then there is CH2 OH. Also here we have CH2 OH. Okay, then there is a hydrogen here, then a hydrogen here. But when you check this one here, and first put a double bond here. When you check this one here, we are going to have, how many carbons are we seeing? There are 4 of them. Then hydrogens, these are 3 plus the 3. Those are 6. Then 7, 8. So hydrogens are 8. Then oxygens are 2. Now when we reduce this to the empirical formula, it is going to be C2H4O. So it's not H5. So that means what we are going to have here, hydrogens must be 10, then oxygens 2. How can they be 10? Is when I add a hydrogen here and when I add another hydrogen there. So meaning this one has to go off Then we have another hydrogen here, and then another one there. You see? Now that means the empirical formula is going to be C2H5O. This thing is going to be the same with this one here. They are going to give the same, okay? Same compound. So this is the same for the reduced product of this and also this one here, okay? Now, they are saying Y can be reduced to compound Q also with the empirical formula. That is true. Then they are saying which statement is correct. They are saying X is a cis isomer. We have seen it is a cis isomer. It is true. So look here and here. Then they are saying compound P and compound Q are identical. Like I said, they are identical. They have the same composition. Okay. This one is just up here. It is cis, but when you reduce, it is going to give you the CH2OH. Okay. The same to this one here. So nothing has changed. Remember, cis and trans, we are looking at this arrangement of atoms. They have the same molecular formula, but different arrangement of atoms in space. That is stereoisomerism. You see that? So our answer has to be A here. Okay? Has to be A. Compound P and Q are isomers of each other. These ones are not isomers because when we reduce to this, we are not going to have cis and trans. You see? It's a diol. Just like this one. They are not isomers. They are all going to have this kind of structure. Okay? So answer is A. Question 39. What is the total number of sp3 hybridized atomic orbitals used in the bonding of but2-ene? So but2-ene, we are having 1, 2, 3, and then 4. So the double bond is in here. Then we have a hydrogen here, and then here we shall not have a hydrogen there because carbon must have 4 bonds. Now I'm just going to consider, remember in hybridization here, an electron is excited from the s orbital to go to the p orbital. Okay, so you are having all of these ones, the electrons fronted for bonding. So I'm going to put for 2 carbons here. So we are having also this. Now for this carbon here, it has 4 sigma bonds. So there is a hydrogen here. Okay, another hydrogen attached to this one, another hydrogen attached to this one. You see? Then there is a sigma bond here formed between these two. So that means there is what we call head-on overlap. Okay, so let me represent it with this one. In fact, let me change the color and make it, let's say, red. So head-on overlap of those ones there. So this is sp3. sp3. So sp3 actually means the orbitals which are involved in the bonding before, that is the head-on collision, head-on overlap before the sideway overlap to produce the pi bond. Okay, so we are seeing 1 s orbital and then 3 p orbitals. They are all involved in that bonding. You see, that is sp3. But if you have something like an alkene, you have this one here. Let me first simplify this one for you so that you understand the sp, sp2, sp3. Now here we are having same thing here, like this. Then also another one here, like that. It's for the carbon atoms. Okay, now this one gets a hydrogen and also this one a hydrogen. Okay, so I'm talking about these ones here, and also another hydrogen here. So these 2 on that carbon, so these are the ones here. Okay, then also this carbon here has gotten another hydrogen bonded here. Okay, now when you see this double bond, there is a pi bond and then a sigma bond. Okay, so the sigma bond is for the head-on overlap. So the head-on overlap Let me say it is this one here. Okay. Now, these ones are left unpaired. So how many are used for bonding to form the sigmas? We have 1 here, 2, then 3. You see? So 2 P's from here and then 1 S. So that's why we say SP2. 1 from the S, 2 from the P's to form the sigma bonds. These are the ones. Then now the pi bond comes in. So these numbers here represent the sigma bonds formed before the sideway overlap. Is that clear? All right. So therefore, now this one is going to be the sideway overlap. So the sideway overlap here, let me actually use this other color. Let me just represent it like that. So that is the sp2. Now, of course, for the sp, for it is going to be, let's say, like ethane. Okay, ethane, like this one here. So you are going to have the same thing here. These are 3 here. You have this, then like that. So these ones are going to have the hydrogens. Also this one, the hydrogens. So for the pi bond, here we have the 2 pi. Okay, there is this vertical sideway overlap, and then there are these horizontal. Okay, sideway over. They have to be parallel. Okay, so when you look at like your table where you're seated, so these ones form the horizontal. Okay, and then there is this one which is vertical, which is coming on top. Okay, this one, the vertical one. Have you ever looked at somebody dancing using the person is here, but when they're dancing, they put, let's say, the wheel of the bicycle. They put it here, then they rotate their waist. Okay, so that's the same thing here. So this one is the sideway overlap horizontally, and then this one is the vertical one. So they are like that. Now, having seen that, so the sigma is here, then there is another sigma here. Okay, remember we represented this one with red. There's another sigma here because I told you here there is 1 sigma bond and then the 2 pi bonds. Now, the ones that are involved in here, we are seeing 1s and then 1p. That's why we call this sp. Now, these ones are going to be sideway overlaps. This overlaps with this sideway, and also this one with this one sideway. You see? But which are the ones involved in the sigma bonding? 1s, 1p. So it is sp. Let me hope you have gotten it. All right. Now let's fall back to our question here. So this is how many sp3 hybridized orbitals? Here we are seeing 4 of them. Okay, 1, 2, 3, 4. Then also this side 1, 2, 3, 4. Those are 8. Okay, sp3 hybridized orbitals. All of these ones you can see. The one we got here, then here, and then also this one here. All of them. So our answer is giving us 8. Okay, for this case. So that's what I'm going to go with. So the answer has to be 8. I mean that D. Question 40. Compound L contains carbon atoms. It is analyzed in a mass spectrometer. The table shows the relative abundance of the only 2 peaks recorded with mass to charge ratio greater than 127. They haven't said that the mass to charge ratio or the molecular ion or the mass of the molecule, the relative molecular mass of that molecule is 127. This was a trick. Okay, so these are the ones here. And when we are finding the number of carbon atoms, number of carbons, we use this formula 100 over 1.1, then times the M plus 1, the relative abundance of the M plus 1 ion, divided by the relative abundance of the M plus. Okay, so when you look at these ones here, the relative abundance, I mean the M plus, since we are using the M plus and the M plus 1, this should be taken as the M plus and then the M plus 1 because they differ by 1 and their relative abundances are given. Now, if you take your M plus to be the 128, which one is its relative abundance? You don't know it, and it is not 50 because this one is given as 50. You see that? Okay, so they have not told you that maybe there is a bromine or a chlorine because those are the ones that give, in fact, these are molecules even. Okay, molecules in here. So because we see for M plus 2, actually it is M plus 2, okay, where we talk about the bromine, because for which it has bromine 79 and then bromine 81. And for them, their relative abundances are all 50%, okay, 50-50. So that means the peaks are of the same lengths. But then when it comes to chlorine, because that one has 35 and then 37, this 35 is it's the most abundant, which is 75%, and then this one is 25%. So that means this 35 is long and this one is short. So this one is a third of this one, okay? But we are not looking at these ones here. So the trick here was to find out which one was the molecular ion. The molecular ion, since we are given the relative abundances here, and the mass to charge ratios are differing by 1, so this is the M plus, and this is for the M plus 1. So we put, this is 100 out of 1.1, then times for the M plus 1, the relative abundance is 5.5, and then for the M plus is 50 here. Of course, this one will go here once, then here 2 times, then 55 divided by 11, you get 5. So we go here 5. So 2 times 5, this one will give you a 10, and your answer becomes a D. So this has been it for this part of the paper. Thank you so much for watching. May God bless you. If you find the content very helpful to you, kindly like, share, and even subscribe. See you in the next video.